very much. Thanks very much for the invitation to speak. And thanks for coming this early to listen to me. So I will begin with a very quick introduction to K-theory. There are many people in the audience who know much more about algebraic K-theory than I do. And then I'll try to get to the recent work and the projections. Okay, so first we have to remind ourselves an exact category should be a category where you know what short exact sequences are. So in an abelian category, you know what short exact sequences are. There are triples like this, where F is the kernel of G and G is the co-kernel of F. And remember, an abelian for a category to be abelian is a property, not a structure. If I give you a category, then either it's abelian or it's not. And if it's abelian, then the exact sequences are defined universally. Now, an exact category is a category where I tell you what the short exact sequences are. It comes with a collection of short exact sequences, and they have to satisfy some axioms. And the axioms are designed so that any abelian category is an exact category, with the usual definition of short exact sequences. And any full subcategory closed under extensions is exact, where the exact sequences in E are those sequences which are exact in E. And for us, the most important example in this talk will be the category of vector spaces over some space. Now, there are many topologies here, so vector spaces come in many flavors. You can look at topological vector spaces on a manifold. Most of the talk, I will look at algebraic vector bundles over ST. Anyway, the next definition is, okay, first there's the example. So given any additive category, you can make it exact by declaring the split exact sequences to be the exact ones. So the sequences which have a splitting are exact. This satisfies the axioms. And most of the time, if I give you some exact category, like the exact category of vector bundles on a scheme, it will not agree with its split exact structure. So for a scheme, E is equal to E plus if and only if the scheme is active. Okay. Next comes Grothendieck K0. This is also old. So if you start with an essentially small exact category, you take the free abelian group on all the objects and divide by the relations that come from short exact sequences. So given a short and admissible exact sequence, you declare that E is equal to the sum of the other terms. And since most of the talk we'll be looking at E being the category of vector bundles over a scheme, we'll adopt the shorthand that K0 of X stands for K0 of vector X. And people will object that the K0 should be a superscript. This should distinguish us from the topological situation. So in the topological, this is contravariant in X, but I make no apologies for this. This is not my notation. So now, next comes the mediatory sequence. So suppose you have a scheme X and it has two open subsets. Then restriction to an open subset is an exact functor. It takes short exact sequences to short exact sequences. So you get a diagram of exact categories and exact functors between the square. Now, if you apply K to it, K0 to this, then you will get 4 abelian groups and a commutative diagram. And with abelian groups, you can assemble any commutative square to a composite you can fold it to get a zero composite. And now the old fact that's been known for ages is that if U and V are a cover for X, then this is exact in the middle. And very classically, people wanted to extend it to a long exact sequence. So for us in the talk, higher and lower, so higher K-theory, both positive and negative, will be some way to complete the Meyer-Viatori sequence to a long exact sequence. Of course, higher K-theory has many other properties, which many of them know much better than me. But for us in this talk, this will be the key property, the long exact sequences. Now, of course, the way topologists customarily do this is by looking at K0 of suspensions and using block periodicity, and then the K-theory is periodic. In algebraic, so when you do K0 of schemes, or Ki of schemes, you're very far from periodic. In fact, there's a strong tendency for the negative K-theory to vanish. So there's an old conjecture of Weibel that if X is an Ethereum scheme of dimension n, then K of X vanishes, Kn of X, or Kr of X vanishes for all R less than minus A. Sufficiently negative K-theory vanishes. This isn't a conjecture, it's a theorem now. So Weibel conjectured it in 1980. There was a string of papers by several people proving special cases, but the general proof didn't come until 2018, almost 40 years ago. And then there's a conjecture due to Schlichting, and this is what I want to focus on more. So Schlichting proved that as long as you have a regular Noetherian scheme of finite dimension, then all of the negative K-theory vanishes. And he went on to conjecture a lot more. So let me explain Schlichting's conjecture. So the observation Schlichting made is that the hypothesis that X is regular Noetherian and finite dimensional are precisely the hypothesis under which K0 of the vector, or K of the vector bundles on X, actually agrees with K of some abelian category, and in fact the abelian category is the category of coherent sheaves of X. And what Schlichting conjectured is that for any abelian category, all of the negative K-theory should vanish. So he made this conjecture in his PhD thesis, which was published in 2006. And for us, for the rest of the talk, it will be conjecture A. So as you can guess, there'll be more conjectures. Okay, so I should say something about what Schlichting proved. So he proved that as long as A is an Ethereum abelian category, then the conjecture is true. And unconditionally, for every A, he proved that K minus 1 of A vanishes. And I should say that there was a plausibility argument that came with the conjecture. So there's an old theorem of Quellens, which says that if you have a triple of abelian categories, so you have an abelian category B, a Serre subcategory A, and you form the quotient B mod A, which you'll call C. Then there is a long exact sequence in K-theory which terminates at K0. So as long as you don't leave the world of abelian categories, you don't see any need for a negative K. So somehow the expectation is that you should be able to construct negative K-theory entirely in the world of abelian categories. And roughly speaking, the way you go about it, okay, so you want to do some dimension shifting, but now what do you want to actually do? You want to embed A into an abelian category with vanishing K-theory and form the quotient, and then you'll apply this negative K, this long exact sequence, and if all of the middle has vanishing negative K-theory. The slanted arrows will all be isomorphisms. It will allow you to dimension shift. And so you want to construct some B with vanishing K-theory. And the natural trick is to try to use Eilenberg swimming. So if you could embed A in some abelian category with countable coproducts, and it would have to have vanishing K-theory for formal reasons. Why? If you have if you have countable coproducts, there's a functor which takes every object B to itself countably many times. It is a coproduct of itself. So this is a functor, and f of b is clearly isomorphic to b plus f of b. You add one more, you don't notice. And when you apply K-theory, this gives you that Kn of f has to be Kn of the identity plus Kn of f. And by the magic of subtraction, you have that Kn would have to take the identity to 0. So this seems very plausible. So given A, you can always embed it into a category which has coproducts. That's stupid. You just take your mega. You can also look at the smallest category that it embeds to with countable coproducts. So it looks like you're home free. But the problem is that A is basically never going to be a Serre subcategory. So how do you see this? Suppose you have some object, and you take a countable collection of morphisms AI to A. Now, in the category B, you can form the coproduct. So the category B has countable coproducts. You can add all the AIs. And in the category B, there's a morphism from the coproduct of the AIs to A. Now, B is an abelian category. You can form the image of this morphism, which is a B subobject of A. And this B subobject is basically never in A. And if you take finite sums of the AIs, the images grow as the sum grows. And you can also see why the Noetherian hypothesis might help. Anyway, so this runs into difficulties. And there the problem stood for a decade and a bit. And the theorem I want to tell you about is a theorem of Antieau, Gepner and Heller, a beautiful theorem which I'll discuss for the rest of it. So, what do they prove? If you take any model category, any stable infinity category, it doesn't actually matter which enhancement you get. You take any enhancement you want of a triangulated category, and you assume that the triangulated category has a bounded T structure. Then the negative K-theory is only defined on the enhancement. But you nevertheless deduce that the negative K, the K minus 1 of T will always vanish, and K minus n of T will vanish as long as the abelian category, the heart of T, is Noetherian. So I will try to explain to you why this is an amazing theorem. But let me first observe that it is a major generalization of Schlichting's old results. So Schlichting's old results are the special case where you take the bounded derived category of A and the standard T structure. Okay, so I should say, before moving on, I should make one comment. So as you can read from the title of the paper by Antieau, Gepner and Heller, this gives you obstructions to the existence of bounded T structures. And I think it's fair to say that until this paper appeared, we all thought that bounded T structures are cheap. It's easy to construct. There are a dime a dozen. There are many procedures for constructing T structures and also many for constructing bounded T structures. I'll come back to this point at the end of the talk. For now, let me point to the generalizations of Schlichting's conjecture. So these conjectures are due to Antieau, Gepner and Heller. There's conjecture B. So Schlichting's conjecture was conjecture A. Conjecture B says that for any T with a bounded T structure, all of the negative K-theory is zero. And conjecture C says that, okay, at least the theorem of the heart should hold. So the map from the K-theory of the heart to the K-theory of T should be an isomorphism. Of course, for n positive, it's known. For n negative, assuming the previous conjecture holds, they're both zero, so of course they're isomorphism. But anyway, just to cover themselves, the authors made this conjecture. And the conjecture comes with a plausibility argument. So let me sketch the plausibility argument. You can do the same. You can sort of do what Schlichting did. You can try to prove it by dimension shifting. So here, if you take R and embed it in an S with quotient T, there's also an exact sequence of the theory. And in order to do dimension shifting, you try to get the K-theory of S to vanish. So you start with an R with a bounded T structure. You embed it in an S with vanishing K-theory. And you try to do it in such a way that T also has a bounded T structure. And then you could dimension shift, because the diagonal arrows would all be an isomorphism. Whatever vanishing you have for T, you forces the same vanishing for R one-dimensional. And as I said before, the world is full of T structures. The philosophy is that bounded T structures are cheap. It's easy to observe. So I should say that the first I heard of this paper was when I happened to be in Boston, and I heard David Gepner give a talk at MIT about it. And that was in April 2018. And then shortly after, David moved to Australia, and he gave several more talks. I heard one in Canberra and one in Sydney. And every time after the talk, I would tell anyone who wanted to listen, this is a spectacular result. And among other things, this proof can't be difficult. Someone should carry it through. But you know, young people don't listen to old ones. So then came the pandemic. It was 2020, and we were all stuck. COVID hit. And in lockdown, there's not a lot to do. So I decided, what the hell? How difficult can it be? Let me try to do it myself. So I tried to carry out this program. How difficult could it possibly be? It turns out not to be difficult, it's impossible. So the conjectures are both false. And the counterexamples appeared last year. And I will try to explain the counterexample because there is the possibility of major improvement. Okay, so let me explain the counterexample. So in order to give you the counterexample, I have to give you a triangulated category with a T structure, and then compute that its negative K-theory doesn't vanish. So first, the triangulated category. I'm going to introduce three triangulated categories. So there's a triangulated category with the bounded T structure, and the other two which will help me compute the negative K-theory. Okay, so let's start with any exact category, any idempotent complete exact. So the first category is the bounded homotopic category of co-chain complexes in. I like to index things chronologically. So these are co-chain complexes in the category E, and the morphisms are homotopy equivalence classes of Cauchy maps. Okay, if you want the enhancement, I leave it to the enhancements. This has an obvious enhancement. Okay, and this has a subcategory, the acyclic complexes. Now you have to be careful. In an abelian category, you're not confused about what acyclics mean. Acyclic means that image equals kernel. Now, in an exact category, you cannot form images and you cannot form kernels of general maps. So how are we going to define acyclics? Well, we define them by insisting that the images should exist. So every morphism delta from EI minus 1 to EI factors through a KI, which you should think of as the image. It's an object in E, in such a way that the KI goes to EI goes to KI plus 1 is an admissible short distance. In other words, all the data showing that this is acyclic is in the category. Okay, so this turns out to be a fixed subcategory of K of E, and you can form the quotient, which I will also give a name. That's the derived category. Okay, so I have 3 categories, and now I need a T structure. So here it is. So just for those of you who are reading this for the first time, the T structure on the triangulated category means I have to give you 2 subcategories. The negative objects and the positive objects. And they have to satisfy some properties. So here I tell you the negative objects are those which vanish in all positive dimensions. And strangely, the positive objects are the ones that vanish in all dimensions less than -2. Okay, now I have somewhat unusual T structures for those who in the know. So I really should prove that this is a T structure. And so to begin with, the negative objects have to be stable under suspension. So if you shift the negative object to the left, it should become even more negative. And the positive objects should be stable under desuspension. And these visibly. Next, bounded. Bounded means that if you take any object and shift it far enough to the left, it will become negative. And if you shift it far enough to the right, it will become positive. And again, this is obvious for this T structure. So what needs proof? Well, the first thing is there is no non-zero map from a negative object to a desuspension of a positive object. So what does this mean for us? It means that any Cauchy map like this must be null homotopic. So a Cauchy map looks like a diagram like this. Why should this be null homotopic? Well, here's the proof. Consider the square in red. It has to be commutative. So the composite from E0 to F1 has to vanish. But the bottom row is acyclic in the exact category E. And the acyclicity actually means that delta minus 1 is the kernel of delta 0. It forces it. So therefore, the map G must factor through delta minus 1. So there is a unique map theta rendering commutative the red triangle. That's some progress towards a homotopy. Now, it's unique. So either I prove that it provides a homotopy or there isn't one. So let's prove that it provides a homotopy. So first of all, the triangle commutes, and I can compose with the delta minus 1 upstairs. You get that the 2 composites from E minus 1 to F0 are equal. Now, if I forget the diagonal map for a second, the red square commutes. So these two composites are also equal. So putting the diagonal back in, all three composites have to be equal. And now let's forget G and look at the two composites which factor through delta minus 1 tilde. They're both equal, but delta minus 1 tilde is the kernel of a map. It has to be a monomorphism. So it forces the triangle to commute. So both triangles commute, and I have a homotopy. End of proof. Okay, in order to complete the proof that this is a T-structure, I have to show that every object is an extension of a negative, it can be expressed as an extension involving a negative object and a positive object. In this form. Okay, so how do I do it? Remember, the maps have images because the complex is assumed acyclic. So I can factor delta minus 1 through its image. And this allows me to form the following commutative diagram. It allows me to form 3 cochain maps. And, well, so it's an exercise to show that the mapping code on this is precisely the middle term, homotopy equivalent to the middle term. And therefore, this is a distinguished triangle, which expresses E as an extension of the negative term by the desuspension of the positive term. End of proof. This is a bounded T-structure. Okay, so I've produced for you a strange bounded T-structure. Now, it would be interesting if I can compute the negative K-theory somewhere. So, okay, let me first observe that the heart of this T-structure is perhaps a little unusual. So, the definition of the heart is that an object belongs to the heart if it's both positive and negative. And in this case, that means it's an admissible short exact sequence in these dimensions. And the morphisms in the heart are homotopy equivalence classes of chain maps. So you discover that this category, the category of admissible short exact sequences, with homotopy equivalence classes of cochain maps and morphisms, is an abelian category. Remember, being abelian is a property, not a structure. I told you the category, it's abelian.
It's surprising, but it doesn't look like an abelian category.
Well, I will not contradict you. Anyway, so next we want to compute K. So remember, I introduced 2 auxiliary categories. There was the category K, D of E, and the derived category. And the point is that because this is a Verdier quotient, they come with a long exact sequence in K-theory. So I don't know how to compute the negative K-theory of the column on the left, but I do know about the negative K-theory of the other 2, because they are just the K-theory of E with a split exact structure in the K-theory of E. So now, if conjecture B is true, then the column on the right, on the left, I have problems with my right and left. The column on the left would be all 0, forcing all the horizontal maps on the right to be isomorphisms. So in order to produce a counterexample, all I have to show is produce some exact category E for which one of these horizontal maps on the right is not an isomorphism. Okay, so that would kill conjecture B.
What's the notation E plus?
E plus is E with a split exact structure. I mean, we met it way back in the beginning of the talk. For any additive category, you can turn it into an exact category by giving it structural split sequences are exact. And this always has an exact functor into E with whatever structure it comes with. Okay. So I have to produce an example where this is not an isomorphism. But now, if I'm into the business of killing conjectures, why not kill two with one stone? So remember that this would kill conjecture B, but there's also conjecture A, which is about abelian categories. That's Schlichting's old conjecture. So if you're going to study Schlichting's old conjecture, then it makes sense to study the map from the K-theory of the heart to the K-theory of this. If we're going to prove this is non-zero, and we know that this map is an isomorphism, then we'll have an example where this is non-zero. So this was a strange abelian category, but it's an abelian category. So if we knew that its negative K-theory is non-zero, then it would kill conjecture A as well. So you can analyze this. The map from the negative K-theory of the heart to the negative K-theory of the cyclics is induced by the so-called realization functor. So this is a functor going way back to the beginning of the subject. There is a functor from the bounded derived category of the heart to the cyclics. And the K-theory of the heart is almost by definition the K-theory of the bounded derived category of the heart. So if this triangulated functor is an equivalence, then the mapping K-theory would have to be an isomorphism. And the theorem tells you precisely when this is an equivalence. So it's an equivalence if the category E is hereditary. X1s vanish in dimension greater than 1. And of course, if it's hereditary, then the mapping K-theory is an isomorphism. So as long as you stay with hereditary exact categories, E, killing one conjecture, well, killing conjecture B also kills conjecture A in the process. And for us, E, throughout the talk, has been the exact category of vector bundles in the scheme. So if you take an algebraic curve, then the category of vector bundles already has this property that it's hereditary. And for those of you who want the reason, the point is that there's a spectral sequence whose E2 term is HI of xj of EE dashed, and it converges to xi plus j. And when you have vector bundles, which are local to 3 sheaves, the local X groups vanish. So they vanish when j is bigger than 0. And as long as you're on a curve, the cohomology vanishes as long as I is bigger than 1. So somehow, for reasons of trivial collapse in the spectral sequence, the xi will vanish for I bigger than 1. This is only true for curves. Okay, so as long as we stay with curves, then we're in business. Killing one conjecture, killing conjecture B will kill conjecture A as well. So now, how does the proof in my paper go? So I specialize to the case of projective curves, and I specialize to the case of projective curves where I find it easy to compute what this negative K-theory is. So these turn out to be projective curves with only single nodes of singularities. And then with some work, I compute that K minus 1 of E with a split exact structure is 0. But there are known examples where k minus 1 of E isn't 0. So this ends the proof. And if we recall the exact sequence, what am I doing? I produce with some effort an E such that k minus 1 of E with a split exact structure is 0. I should be able to shine a light on this. This one vanishes, and therefore this diagonal map is an injection, and there are known examples where this is non-zero, so then that would be non-zero, giving a counterexample to both conjectures. So this is the way the argument works in geometry. And what can I say? It's a lousy argument. So what precisely does this mean? It means that since publication I found much better. This is lousy quantifying. So what is the part that I do? The sad thing about the published paper is that you can no longer edit it. But what would I do if I could? So the part I would change is the part in orange. So there's a much better result. And the much better result runs as follows. Suppose E is an idempotent complete additive K-theoretic, right? Just an idempotent complete category, additive category. Then as long as all the endomorphism rings are Artinian, the negative K theory all vanishes, not just K minus 1. So what can I say? In hindsight, you realize how stupid you've been. So not only is this true, it's a far more general statement, it's true and easy. So why is this? If you take any object in E and look at its endomorphism, then call it R, then the category of finitely generated projective modules over R is isomorphic to the category, it's equivalent to the additive category that you get by taking the object and taking all finite direct sums and direct sums. And so if the endomorphism ring is Artinian, then it's an old theorem that its K theory vanishes. And now, so this means that as long as all the endomorphism rings are Artinian, the category E has lots of subcategories with vanishing K. And as these subcategories form a system which exhausts the category, if you take bigger and bigger direct sums, the category is the filtered colimit of these subcategories, and therefore the K theory of the category is the filtered colimit of the K theory of the subcategories, and that's 0 in negative degrees. So not only is this better theorem true, it's true and easy. And why am I telling you this? Because if you go back to the long exact sequence, then this provides many examples in which the middle column is 0. As long as you can guarantee that the endomorphism rings are all Artinian, the middle column will have to vanish. So this means that all the diagonal arrows will be isomorphisms. And there are many examples in which the right-hand column is being computed and is now 0. So this gives you lots of examples, lots of counterexamples to conjecture B. So we already know that conjectures B and A are false, but we don't know about conjecture C. And now that we have so many candidate examples, we could test it. So for those interested, conjecture C is still completely open. And here is a treasure chest of possible counterexamples. Of possible test cases. I mean, I shouldn't say that I expect the conjecture to be false, but
But you're sort of hinting that.
At the very least, someone should check. Because, yeah. Anyway, so I've talked long enough about. So, okay, let's go back to the theory. So
just to check, so like in that theorem, you don't need like two objects E and B prime.
yeah, that's right. Of course, if you know for every E, you know it for E plus E prime, so that's it's not very different, but you don't need to be linear over it. Okay, let's go back to the theorem of Antieau, Gepner and Heller. I mean, until now, I spent basically the entire talk looking at the K-theoretic side. So this is a theorem about vanishing in K-theory, and you can ask yourself, can you improve this K-theoretic statement? So maybe, but the conjectures made in the paper were a bit too optimistic. But there's another side to it. This is a spectacular paper, and it has the K-theoretic side, but there's also the obstruction to T-structure side. It tells you that some bounded T-structures cannot exist. In particular, if you let X be a finite dimensional Noetherian scheme with an I, if you don't let X be a reasonable scheme, then the conjecture says that if K minus 1 of X is non-zero, then the bounded derived category of vector bundles on X cannot have a bounded T-structure.
That's what the theorem says. You said the
Yes,
conjecture.
that is a corollary.
Corollary, exactly.
Yes. After all, this is, yes. And if Kn of X is non-zero when n is smaller than or equal to -2, then it tells you that if there is a bounded T structure, it better not have an Noetherian heart. So this is in the paper by Antieau, Gepner and Heller. It's corollary 1.4. And they go on to, the authors are brave. They go on to formulate a brave conjecture. And the conjecture was that if X is a finite dimensional Noetherian scheme, reasonable scheme, then the category of the bounded derived category of vector bundles should have a bounded T structure if and only if X is regular. So on the basis of the obstructions available at the time, this was a daring conjecture, but anyway you can find it as conjecture 1.5 in this one. And what can I say? The most wonderful conjectures are the daring ones that turn out to be true. And this one is one. So the theorem is even more gentle. It says, suppose X is a reasonable scheme and Z is a closed subset. Then you can look not just at the vector bundles of X, but at the relative case. So you look at the boundary derived category of vector bundles of X, whose cohomology is supported on Z. So the way to say it is that if you restrict to the complement of Z, you get something basic. Okay, so when Z equals X, this is just the old one, but we're now having a relative version. Then the assertion is that this category has a bounded T structure if and only if Z is contained in the regular local surface. So you can find this theorem and its proof in this paper. And it raises several questions. So the first one is, what is the real obstruction? So what have we learned? We have learned that having a bounded T structure is obstructive. Negative K-theory contains obstructions, but there must be others, because this theorem tells you, for many of these, there is no K-theoretic obstruction. But nevertheless, there is no bounded T structure. So, for those of you who work on motives, you might care whether the conjectural bounded T structure on motives, on the derived category of motives, is obstructed. Once you have an obstruction, you can check it in other situations. There is an obstruction. As far as I know, no one has computed the negative K-theory there, but who knows, maybe it is an obstruction. And maybe there are some other obstructions. By now, okay. So there are many categories that are conjectured to have bounded T structures, but the bounded T structures would be very interesting to find. And now we know that this is obstructed, and we don't fully understand the obstructions. Okay, so I should probably summarize all of the questions we have in the talk. So, first, way back, the theorem, actually let me go back a little way, we'll find the theorem of Antieau, Gepner and Heller. So, there are several things about this theorem. The first is, there is an obstruction to the existence of a bounded T structure on T, but the obstruction that the people in the back found is in the negative K-theory of T, which is defined in terms of an enhancement. You need an infinity. The world is full of DG. You need some enhancements. The world is full of different enhancements, and it's entirely possible for categories to have different enhancements. So in principle, it would be possible to have one enhancement with vanishing negative K-theory and another with non-vanishing negative K-theory. So explain this. You have the obstruction is to something that's purely triangular in nature, but the group in which you compute the obstruction is actually depends on the enhancement. So this is number one. Number two is that there must be other obstructions. So that would be very interesting to understand. Number three is there is the conjecture that turned out to be false, that a bounded T structure would imply the vanishing of all of the negative T. On the other hand, the theorem is strange in nature. So it tells you that this is true as long as the heart is Noetherian. But K-theory is, after all, self-dual. So the K-theory of the dual of T is the K-theory of T. So that also means that for Artinian hearts, you will have vanishing K-theory, and therefore for any hearts that are assembled from Artinian and Noetherian. So there must be a true theorem, and it must be more general than the one before. So find the right statement and prove it. And yes, I should probably stop. Thank you very much.